So Richard Taylor, it's a pleasure to meet you. We're sitting here just across the road from Stanford campus where you spent most of your research life, but you're actually a Canadian and were brought up there, spent the first 2 decades there.
That's right.
You come from Medicine Hat, Alberta, which was a town that was transformed by the Second World War. Could you tell me?
Certainly changed a great deal because there was a British flight training school for the RAF, not the Canadian Air Force, but the British Air Force. And then a little bit later there was a prisoner of war camp with a population almost equal to that of the town of German prisoners, and also prisoners of many of the surrounding countries who'd been pressed into service in the German army.
So these are prisoners who had been shipped across to Canada?
Shipped across because, it was difficult to get enough food to England. The boats came back empty. So it was easy to bring the people back and save the food, put them where the food was. So they did that. It was hard to escape. In the middle of Alberta, I think there were 3 people who walked across Canada and got back to Germany. Toward the end of the war, there was a Defense Research Board station for biological and chemical warfare put on some of the spare land outside of the town. And so that's the first time I ever saw a PhD.
So this was a massive influx of culture.
Yeah, just completely different kinds of culture altogether.
So did your interest in science start with this influx of people, or was it?
No, I don't think so, not particularly. I think even before that I had started to, I was curious about things, and I had started to, in the sort of children's books, like the books of knowledge, I was interested in the little scientific blurbs that come in there from time to time. But certainly it was during the war that, because that's when I was growing up, that I became interested, and we had a library in the town. I remember reading books by Jeans and Eddington, and popular books about astronomy and stuff. That certainly affected it. But I assumed when I was young that I would become a surgeon, and I was quite shocked when one of my surgeon friends, after I blew the fingers off my hand, the surgeon said, people aren't going to come to a surgeon without fingers.
So
I had to give that up. But I went to university. I did not matriculate from high school. I failed Latin. But somebody talked me in, the principal, I guess, talked me into the university. And I took physics just because I had best grades in physics. Mathematics was fairly easy in high school, although it got hard later on. And I went into, they let me into honors physics at the university. And there I guess there was this was just after the war, there were a lot of students. So people were kept on, and there was one old man, probably past retirement, who was a real physicist, who had publications that you could find in the journals and things like that. And he was an experimentalist, and I really admired him. And he taught optics, and I could not believe the things that he did in the optics labs. I thought they were just marvelous. And so that probably had more influence. The chemistry teacher in high school, and then the optics teacher at the university.
Okay. Well, just back to the chemistry teacher in high school and that
Yes.
lasting.
Well, I was very interested in experiments even then, and I had a laboratory at home, which was you couldn't reproduce today because you're not allowed to have most of those chemicals in a home chemistry set anymore. They're very dull chemistry sets now. And I used to do a lot of experiments in the basement, and I started playing with black powder, like many of my experimental friends in high energy physics. And then some of the boys that worked at the Defense Research Station brought home a recipe for smokeless gunpowder, which was much more powerful. And I could have easily made enough to kill me, but I made a small amount, and the small amount exploded on me and took off my fingers and messed up quite a few other things, in fact.
But didn't put you off, that experience? No.
Put me off chemistry.
Okay. So it's a balance between the chemistry teacher and an explosion, and
right.
that adds to physics.
And well, the chemistry teacher was, probably shouldn't say it, better than the physics teacher in high school, and so I admired him more and learned more from him, actually. And so then at university I was in honors physics, and then the honors course was 4 years long, the regular course was 3 years long. And at the end of the 3 years, in the last half of the third year, I was ill for quite a while. I was in the hospital for weeks. But independent of that, I had never really done all that well in the math. So they bounced me out and gave me the unhonors degree. And I just went back and took the same courses in a master's program the next year. So in the end, it saved me a year's tuition at Stanford. But so I didn't graduate from high school, thrown out of the honors program. Now the students, my fellow students from the honors program, right, now go around saying, well, it was quite a good group of people. There was only one guy flunked out, and he went on to win the Nobel Prize. So that was there, and by that, then I went back to work in the summers at the Defense Research Board, and my boss there, who was a physical chemist, the second year, when I was working on the master's, said, well, next year, when you got your master's, you could come back here and work. But if you're serious about physics, you got to have a PhD. And I sort of said, what's that? And he said, well, you have to go to do some research. And to do it, since Alberta didn't have a PhD program at the time, you'll have to go to California or to Eastern Canada, Toronto or something like that. For a Western Canadian, that's not a hard decision. And so I wrote down here. And as I say, my grades were not that hot. Berkeley just said no by return mail. But Stanford was quite different in those days and paid a lot of attention to written evaluations. They didn't, what the hell do they know about the grades from some little university in Canada? So what do people say about this fellow?
That makes sense.
And again, the physical chemist in the Defense Research Lab actually had quite a few connections here at the Stanford Research Institute and probably with Stanford. So I suspect that's what happened, but I don't really know. Anyway, I was admitted here.
Can I just were those very different days then? Does that
Stanford was not the great school that it is now. It was starting to there were some very good people here, but the reputation was still that it was a country club school where rich young San Franciscans went.
Right.
In the 50s, Stanford started using its endowment, federal research money, and its climate to improve the faculty. And over the next 15, 20 years, they did a really good job. And Stanford became a better and better school.
So it was a great time to get in when you came.
It was nice, yeah.
And what was it like arriving here?
Well, it was a big change in the weather to start with, and but also in the school. I mean, there were several remarkable professors here even then. One of them being Felix Bloch, another early Nobel Prize winner, and Panofsky and Schiff. Those people, they were really good professors, and I had a hell of a time catching up. I mean, they asked me, have you had quantum mechanics? Have you had electromagnetic theory? Oh yeah, I've had those things up at Alberta. And I went to class for 3 weeks, and I went back and said, okay, I haven't had those things. I went back and took the whole first year of graduate school here over again.
But nice that you had the latitude to do that. You could just take your time over.
Well, there was a remarkable man here in charge of the department. I remember going to see him one day and saying, just sticking my head in the door, and the secretary saying, "Can I see Leonard Schiff?" And she said, "I don't know." And she stuck her head in his door, and he said, "Come in." And so I sat down, and he knew every grade that I'd had in a year and a half here. Wow. There were 20 students a year or more, but he knew every grade that I had in every course. And it's remarkable to this day that he was keeping track of the students to that extent.
Do you think he saw potential in you, a particular potential?
Maybe it's the first time I remember wondering if I was going to be any good at this business was a day when, in one of his classes, quantum mechanics, when on the way out, he said, "Why do you always sit at the back of the room? You should sit at the front of the room." That was a hint, it seemed to me. So maybe, but I don't. But I was not a good student. I'm not a particularly good student here. I mean, I was average.
When you finished your thesis work, you went to France for a while.
No, before I finished my thesis work, I went to France. I finished the thesis. That's not really fair. I finished the thesis work. We had written the paper, but I hadn't finished the thesis. And the French came and said they were building an accelerator bigger than the one we had here, which would be the biggest in the world, and would I come and help put it together, and would I come quickly because they were going to run in June. And so I just dumped everything and went to France. And I got there, I walked into the hall, looked up and down, and I said, this was July when I got there actually. I said, "This damn thing won't run for a year." And I was wrong by about a day.
Aha. Well,
So they were just tremendously optimistic, and so I should have stayed and finished my thesis. But I came back after a year or two there and worked on the thesis, but I didn't finish it until I actually came back to the United States.
But you must have had some kind of rare ability to put these things together, that they came and sought you out as a graduate student.
No, I think I had some reputation in the laboratory as having been fairly general, worked on the accelerator and on some of the equipment, and able to build stuff. But no, I don't think I was even the best choice. But it was suggested to them, and it's sort of a contest as to who found me from France.
Right. Right.
Later on, it was a contest, not at the time. So I went to France. Again, that's very lucky, because I was right in the middle of finishing an accelerator and getting the experimental equipment ready. And since I was the quote-unquote expert, I was involved in things that no postdoc would usually be involved in. So I learned a tremendous amount about, and I needed to learn a lot. I was an arrogant young bugger. And it was interesting in France. I mean, the differences between the way the lab worked here, the way the lab worked there, made me think a little bit about actually how people did things.
What sort of difference?
What sort of they're much more. They were much more formal than we were, and they were also much more. They used industry much more than we did. We built almost everything ourselves. They used industry, and I made friendships both in the lab there and with the people from industry that were there that last until now. And there were some very bright people in the industry. And so that was very educational, besides all the things you learn if you move to a different culture.
Sure. It's also an industrial scale of construction you're dealing with.
Yes.
So you're learning the skills of project management as well on a very large scale.
Yeah, we didn't talk about project management much in those days.
They do all the time now.
Now they don't talk about anything else, and
Yeah.
they don't really manage the projects.
Why do you think that, just jumping onto that question, why do you think that's occurred? Why is it so much the fashion?
It's because the governments in all countries have become much more sensitive to what they call accountability. And so they control the things that they know something about, which does not include the physics and the science. And so you'll see them have a laboratory with a budget of over $100 million a year, whose job it is to find things out and tell everybody else about them. And they will cut the travel budget so nobody can leave the laboratory. It doesn't really work, huh? So I think the answer is they control things that they think they understand. And so the control just interferes with getting things done much more than getting things done. Because in general, government support of science is a matter of mutual advantage. I mean, the scientists are not doing it because it's advantageous to the country. They're doing it because they want to know. And the government is supporting it because they have found that very often the things that the people want to know in science turn out to be very, very important economic.
There's economic benefits to be gained, but one doesn't know where they're going to come.
You don't know where they're coming from.
Yeah.
You know that they have come in the past, and of course the counter argument to that is, yes, they came in the past, but in the past we used to give people $1 million, not $100 million. So you have to be more careful now, but being careful, if being careful means that you don't find out things, it's not such a red hot idea.
Well, back to the happier days when accountability was less. You spent 3 years in France and then came back briefly to Berkeley and then back to Stanford in '62.
Yeah. Well, the Berkeley experience was interesting. I had a good time there. We did some nice work. But it seemed to me that Berkeley by that time was fairly old. And so he went from me to my boss to his boss to his boss. Eventually he got to one of the Nobel Prize winners at Berkeley. And I didn't like that. It just seemed too cumbersome. So I didn't like the lab as much. I liked Berkeley, this town, actually better than here. But when SLAC started, the big accelerator at Stanford started, I came.
So Congress passed the funding for SLAC in 1962, and it was 5 years later that it opened. So when you came, were you aware that it was on the way and you were moving here?
Well, it was on the way before I came home from France. I knew that. I mean, it wasn't voted on in Congress, but it was. I think it was earlier than that Eisenhower. Yes, it was, because Eisenhower is the one that brought it up, and he was gone by 1960. So it actually was 59 through 62, and the final approval came in 62. But it was known that everything was going in 61.
And one should just set the ground by saying this was going to be the biggest accelerator in the world, 2 miles long, and
yes, it was going to be the most expensive accelerator ever built. And there's always been a split between the East and the West in the physics community in this country, starting with Lawrence and Rabi across the country, and then I think the Easterners were just didn't believe when the boss here, Panofsky, realized that the government might be good for $100 million. Physics in those days was still all at Berkeley. Berkeley was finding all these particles that look like protons and neutrons, but are heavier. Right through the 50s, every month there would be some new particles from Berkeley. It's an incredible time.
once the funding was secure and it was coming, there must have been, I want to imagine there must have been tremendous interest in getting into the facility. Lots of people trying to get,
No, not physicists anyway.
Really?
Well, a lot of our engineers came from Berkeley because they had just sort of finished a project in Berkeley. A lot of them came to us from Berkeley. We were connected to Berkeley fairly closely. So a lot of the engineers came from there. We had trouble recruiting people because it was going to be 5 years before they would get any physics results. And I knew many people who said, oh, I couldn't possibly come to SLAC now because I'm working on the most important experiment that you can imagine at Brookhaven.
So again,
and so I couldn't possibly give that up in order to make this thing.
So again, that points to slightly different days, because now, for instance, the Large Hadron Collider is coming, and people have been talking about it for a long time, and they will be talking about it for a long time. It says people are making long-term plans based around it. It sounds like then things were perhaps moving faster, so that 5 years was a different...
Yeah, the time scale was shorter, but it was still pretty good. I mean, most people did not want to just build the accelerator for 5 years. I didn't think of myself as particularly good at the kinds of things the machine was going to do, and I felt very strongly that we had to build as good a machine as we could build, and I worked very hard on first the end piece of the machine, the thing that spread beams around to different physics, and then on the particular apparatus that we built to do all the scattering experiments.
And it opened in '67. Now,
we started doing things in '66, actually.
Okay, but nobody cut the cord until
Well, yeah.
Yeah. So we're now turning to the work for which you were awarded the Nobel Prize together with Jerome Friedman and Henry Kendall from MIT. And
well, not quite. I mean, we built this piece of apparatus in collaboration. Actually, it should go back. We were building equipment for the delivery of beams from the accelerator. And the question is, what are the beams? What experiments are you going to do? And one group, who was run by the head of the laboratory, was to do electron scattering. Another one was to do photon physics, and that was Bert Richter. And that would be with the same apparatus that I was building. And he was helping, but he was also interested in this other kind of accelerator, the colliding beams. So he was sort of riding along with me for a while. And then Henry Kendall and Jerry Friedman, who had been at Stanford at the smaller accelerator, came back from their jobs at MIT. They still kept teaching at MIT, but MIT was clever and said, okay, the two of you behave like one professor. One of you can go out there and work, and the other one can teach, and then you can turn back and forth. And that was clever of them.
It's a nice early example of job sharing, all the rage now.
Yeah.
Yeah.
And so we had one of them, and Henry Kendall did a great deal. And they built the counters, and Henry did a lot of the electronics that we built to go along with that. And we built these huge spectrometers that, at one point the Smithsonian asked for the spectrometer, said could they get one of the spectrometers, and they didn't give up until we pointed out that they weighed more than a destroyer.
Yeah, where are you going to put it? Yes.
Well, what floor have you got that will support it? That's the main thing.
Yeah. They're hugely tall. How?
Yeah, well, they're about 2 stories tall. I mean, it would have been a lot taller if we had followed the standard design up to that time, which was a 180-degree loop. And there was talk about that for a while until one of the engineers drew a picture of this thing sitting up in the air with clouds going by halfway up. And somebody else pointed out that you'd be able to see this from Berkeley up in the sky. And so it actually took quite a while because I didn't have a good idea as to how to build the one that would go very high. And there were a lot of bad ideas about how to do it and keep it low, and I kept stalling and not making a decision until finally Bert and somebody else, Carl Brown, came up with a smart idea to keep it low, and we built that. So it was really, I was finishing up the end piece of the accelerator and building the equipment for these experiments. When the experiments started, when the machine was finished, the experiments began, we did the standard experiments that Hofstadter had done that looked like they would be interesting. And also you could excite what were called resonances, which were by that time considered particles. And we wondered how those particles behaved when we hit them, comparing them with a proton. And that's what the spectrometers were designed to do. And those experiments were not very interesting. I mean, they were interesting, but they didn't change anything. If you extrapolated Hofstadter's results out, we were right on top of them. So we didn't learn much in those experiments. And then, the policy committee was not too hot about us doing the deep inelastic. They said there won't be anything there.
So I want to ask about this because what you were looking for when you were looking for these large angular deflections was a point-like structure within nucleons, within neutrons and protons.
That's what we found.
That's what you found. Okay, so with hindsight, that's what you were looking for, if you like. But you, as you were about to say, you weren't looking for that.
We thought it would happen sooner. That's the difference, right? We thought we would see point-like thing. There was a picture of a proton when we began to build the accelerator. The picture was that the proton would have a center, which was the real proton, and there would be a cloud of pi mesons running around it. And so it'd be a little bit like the atom. There'd be a center, and there'd be these things running around. Okay, and so they didn't find a center. Hofstadter didn't. He found an extended thing. And we said, oh yeah, he's seeing the cloud. He doesn't have enough energy to see the inside, and we'll get enough energy with the big machine. However, in the meantime, there were accelerators built, round accelerators, built at Boston and in Hamburg. And these went to 5 times the energy of the one out here. And they didn't see an inside either. But we were still hoping that there would be a little inside that we would see, standing still inside the proton. And we didn't see that when we started. That was disappointing. But there were still all those resonances, and it was going to take forever to measure them all and see whether there was something interesting in the way they behaved. And then just because we could do it, it was very easy. The equipment was way more powerful than necessary to do the deep inelastic experiments. And when we did those, they were surprising. And there was one theorist, Bjorkane, who had predicted that maybe it would look like that.
And he was here.
He was here.
Yeah.
Well, he was here. He'd been a housemate of Henry's. And we had 3 bachelors that waited a long time to get married. And they lived in a house together. And they were all climbers, alpine climbers. And so we were all fairly close. And BJ was at Stanford with me as a student. So we all knew each other quite well. And BJ was very good. And he made this prediction, and nobody paid any attention to it, almost including BJ. I mean, whenever he was pushed, he backed away. He said, well, I don't know. I don't know whether it's right or not. And then it was right, and it was remarkable.
So there was a hunch there. There was a hunch.
It was more than a hunch. It was a calculation that I can't understand at all.
Again, with hindsight, it's interesting that the quark, which is something that your experiments reveal the presence of, had been proposed in '64 by Murray Gell-Mann, but actually wasn't at the bottom of these experiments. People didn't really think that the quarks, if they were there, were going to give the sort of behavior that you saw. Or rather, you weren't...
No, a lot of people didn't think there were quarks. Okay, but I got to know Gell-Mann when I was in France. more or less socially. I mean, we weren't collaborating on physics or anything. The families used to get together, and we had a good time. And this was the time when Murray was taking all these particles that had been discovered at Berkeley and other places in the 1950s and classifying them in almost the same way that Mendeleev classified the elements 100 years before that. And then in the classification scheme, people actually knew that there was something three-like about it, right? But in order to have quarks, you had to believe in fractional charges. Nobody liked that. So it sort of sat there for a while until Murray, I guess, I don't remember the story. You can ask Murray when you talk to him. Anyway, he and George Zweig independently, George was at CERN, but they were both from Caltech, but George was in CERN. They both came to this idea that if you took three particles with fractional charges, you could build all of these particles, just like protons and neutrons and electrons could build all the chemical elements after a while, and explain why Mendeleev table made any sense.
If you like, it's a further subdivision of the periodic table, you could say.
Yeah. It was similar to the periodic table in that they found a way to classify it, and then from the classification were smart enough to see a little bit beyond it, which I guess Mendeleev was not. Because it was Rutherford that found that.
That's right. In 1911, he published. He published the existence of the nucleus of the atom. Yeah.
The idea that there was a nucleus and electrons zipping around, and so, but the quarks were suggested by Murray in order to do this, and by George, who called them aces, by the way. And
so there wasn't a general belief that was the right solution.
Well, no, a great many people believed that in what was called dispersion theory, where everything was, and the bootstrap from Berkeley, where everything was made out of everything else, and there weren't any subparticles. Right. And people were nervous about the quarks. I mean, if you read the 1966 conference, nobody is claiming that the quarks are necessarily real. Now, I was fortunate to be able to talk to Murray. And Murray, in those days, said, yeah, they can be real. They don't have to be, but they can be real. But of course, we were looking for, everybody was looking for a quark that you would bounce off the quark the way you bounce off a proton in a carbon nucleus. And you get a quasi-elastic peak, so-called. So you'd have a peak where you elastically scattered from the quarks. And of course, that's what's happening, but nobody thought clearly, until Feynman actually, that these quarks would be moving around at quite a clip, and you wouldn't get a nice peak, it would be very broad. But it was necessary for BJ to point out that we might see that. And we might see a behavior of the cross-section, which implied point-like, and it didn't have to be quarks, right, at that point. Quarks don't come from, we don't show, certainly in the first experiments, we couldn't identify the quarks. We couldn't say we're scattering from quarks. We just said we're scattering from something small. That's about all we could do. And then Feynman came along and said, well, you're scattering from parts of it. And then he drove Murray crazy by calling them partons. When by that time, Murray was pretty damn sure they were quarks.
Okay, so you're gathering these experimental results over a period of just a few months, really?
No, the first experiments didn't even distinguish. They looked like the things BJ was saying, but it was absolutely trivial for anybody in the dispersion business to write it down a dispersion theory which would fit all of our data at that point. It was only a year and a half later, when we did large angle scattering, that we could actually cut the dispersion theory and say, no, that's wrong. We must be scattering off small things. And by that time, well, we talked in Vienna in '68, and Don Perkins went back to Oxford. He was a professor at Oxford, and threw our data on the table to his students and postdocs and said, if that ain't a quark, I don't know what is. So there were quite a few people who went home, took BJ very seriously, and started working on parts and what kind of particles they were. And because you could do, if we were right and we were scattering from these things, then you should also see similar effects in neutrino scattering, which is much harder to do. But they went back, and Perkins did this, they went back and analyzed their neutrino experiments. And there was you should have been able to see results that were connected, but if you drew the two graphs, one of them would be 5/18 as high as the other. And I can remember when, well, since we were the 18, I always thought of it as 18/5. And I can remember when they came up and said, yes, here we are at 18/5. And that night I slept really well, because I was pretty sure then that we were actually dealing with quarks and nothing else.
Yeah. It strikes me that there was quite an open dialogue going on during all this time. But you've been mentioning lots of names. Lots of people were talking about the data. There doesn't seem to be a worry on your part that anybody was going to scoop you or anything like that. It was all...
Well, my job was to measure things and make sure that the measurements that I made were right. It's the job of the theoretical community to understand why things are the way I see them when I do the experiments. So I was not running around saying, I have discovered quarks. I was running around saying, we have very large cross-sections down at the bottom, and I'm pretty sure that they come from this process and not from some other process. And I'm being fooled somehow in my analysis of the experiment. So I'm telling you how electrons scatter from protons. You're telling me what's inside that scatters the electrons. And I don't, so I didn't have any real stake. I mean, the people who had a stake were the people who said, no, there's nothing in there that you can scatter off. They're the ones who were disappointed.
That's a very clear division, very clearly stated. Is that division still the same today?
It's worse.
Right.
It's worse. I would say now, well, there are many people who don't see it as clearly as I do, and fancy themselves as being able to explain to you why the data is the way it is, not just what the data says. And they make fools of themselves once in a while, and sometimes they're very good and they're right. But there is a big division. In fact, the division is even bigger than that now. There's a third group in the middle, which is phenomenologists that try to assemble the data into pieces that make a little more sense than just the raw numbers. And as the experiments get more and more complex, that becomes a more and more important thing to do.
So there is somebody. It is important to have a group who bridge the divide. Yeah.
Yeah, and usually they're in the group actually. And but then there are these pure theorists that have to figure out why. So I know, but I was never worried that I was going to scoop Murray. I was very glad that he was interested in what we were doing.
I read an article that mentioned that you stuck a note to your mirror the day you were awarded. You heard you'd been awarded the Nobel Prize. Well, could you remind me what that said?
No. What I said was, I looked in the mirror and I said, what did I say? I said, Murray Gell-Mann is smart. Dick Garwin is smart. You are lucky.
Yeah.
That's what I said, and that's true. Everybody else is like me. I mean, you give me a problem, I process it with all the experiences I've had, and I try to figure out where it fits and spit out an answer for you. But those guys can really use the logic that's in their brains to work from the bottom up, and I find that an extraordinary talent. The Nobel Prize started when a man and his graduate student did an experiment and told you about it, or in the limit, maybe there was a postdoc in the way, like Rutherford. I mean, Rutherford, Geiger, and Marsden did experiments. Now, here we are, there were 20 of us named on the experiment. Comes from a group that was more like 40 that built that piece of apparatus, backed up by another 40 engineers and technicians, and using an accelerator that's built by 1,000 people. Now, it doesn't work anymore, and presumably at some point the Nobel Prize will look at these kinds of experiments and treat them the way they treat the Red Cross or the Doctors Without
Frontiers,
Frontières.
Yeah.
So they will award it and tell somebody to come and get it, but it'll acknowledge that it's not the work of an individual person, but of a huge group of people. And there's no way. I mean, there's no way to do it fairly with three.
It's an interesting challenge for them ahead. Yes.
Yes.
Yeah.
Yes, because there still are cases where there's one or two guys. So you can argue on both sides, but it's clear that it doesn't fit the kind of experiment that we did very well. I mean, I'm not ashamed of what I did on the experiment, but it's clear that my boss, who was running the laboratory and quit the group just before we did these experiments.
That's Panofsky. Yeah.
Yes, was. I mean, without him, none of this would have happened. I mean, he built the accelerator. He ran this group for a while. He was so. I mean, it's paradoxical that he. Well, I guess as deputy director, when he was eulogizing him, said that Panofsky had more or less deliberately avoided getting a Nobel Prize.
It's a nice thing to say about somebody.
Yes. I don't think it's true, but it's a nice thing to say. But he was perfectly happy. And somebody saw him actually the day he was going to Stockholm, because he came to Stockholm as a guest of the foundation. I mean, he wasn't on the paper, so there's no question.
No.
Right? But they understood what was happening, and they invited him. And he was very proud of the fact that he had 4 distinct Nobel Prizes in the laboratories that he ran. I mean, different experiments.
Yeah.
By different people.
Yeah, and indeed SLAC itself has produced 3 different prizes. Yeah, so.
All while he was director.
Yeah. I want to go back to the experiments in 67 and 68.
Yes.
There was unprecedented precision in the measurements you were making, wasn't there? It must have been.
Well, there was a lot of precision in the apparatus because we were trying to do these elastic and resonances, and those are very narrow. That is, they happen just at a particular energy. So we didn't need that for the deep and elastic experiments. What makes me, what I think we did right was, it was a fairly early application of a large computer dedicated to an experiment, and it made it quite easy to figure out what answer you were going to see while you were sitting in there measuring. You would do a more sophisticated analysis later, but the computer let you do a reasonable analysis right away. So we could follow the experiment while we were doing it. And it was rather than precise, I would say it was efficient. We could measure an awful lot of stuff very quickly.
I just wanted to ask about the equipment a bit. To achieve that, it was very sophisticated equipment building, and you for instance were building the detectors here, the spectrometers. That requires an extraordinary amount of confidence, I would have thought, to pull that together. You'd become a very confident experimentalist, a very confident equipment builder.
Never thought about it. No, I don't think so. I mean, it's true that I was, as I said, I was arrogant, and I wasn't consumed with self-doubt or anything like that about the money I was spending or anything else. But it seemed, I would say, it was just a straightforward attempt to make the apparatus, and I thought I was doing it fairly cheap, and I mean, it's a question of working out what the parameters that you have to have, and then that unfortunately determines how much these things cost. And you could have done things a little cheaper, but it's an optimization problem, and I wouldn't have thought of myself as supremely confident, but I would have argued that to do less was not economical, and to do more would get you in serious trouble. So it's just trying to figure out where you are.
So you mentioned the disbelief of people at CERN. It is, in a way, by 71 or 72, the evidence was so strong. It becomes a bit sad.
It was theorists.
Yeah. Okay. The linear accelerator proved itself pretty fast, because Richter and your results were both fairly stunning in the first few years.
Yes, and so was the bubble chamber work in the first few years. Some of the work was a gorgeous experiment where they had some polarized gamma rays making things in the chamber and showing that the lobes of the production corresponding to the polarization. That's very beautiful stuff.
So I imagine that in contrast to your description of while it was being built, people not wanting to come across and having to suddenly everybody wanted to be there. Yeah.
Well, not even, because a lot of people didn't feel that they had much expertise. Most people had been brought up, on proton machines, which are quite different in the way you use them. It's true we had lots of people trying to come, but there were lots of people who didn't want to mix with us, right? Because there are two things. One of them is the duty cycle is very bad. That is, the machine just comes on for a little tiny microsecond and then goes down here and then another microsecond. And it's only on a very small fraction of the time. So that means backgrounds and everything are very different than they are in a proton machine where everything comes out smoothly. And so many people weren't comfortable with kinds of things. I mean, you have to do things in a specific way. And a lot of the skill from the proton machines did not apply.
But given that experimentation becomes so dependent on access to facilities like this, I was going to ask about resource allocation. If you've got lots of people who want to come and work, how is it decided who should be allowed to?
You have you make a committee. And in this case, you usually make an advisory committee. They consider all of the things that people are proposing, and they tell the director what they think he ought to do. And he usually accepts what they tell him, but sometimes he doesn't. If, in his view, that probably won't work, or if it's more expensive than he thinks it's worth, or if he thinks there's something he should do that they don't think is particularly important. So the director gets the final decision, but he pays a lot of attention to the program committee, who usually do a lot of work. And then you have to have people inside the laboratory who actually figure out how much work it is to do the experiment that these people want to do.
Your work on the quarks went on for several years after the initial discovery. What was there still to find out?
Well, we were doing everything that we originally planned to do. We measured all the resonances, and we measured the deep inelastic where you saw the so-called quarks, and the elastic scattering. All that was done. I mean, you took this rough picture, and that was enough to make people interested. But you want to do what you set out to do, which is measure this thing and see things. And of course, things were happening. When Bert and Sam Ting discovered the psi, everybody wondered if you could see it in the spectra, in the inelastic scattering spectra. We did an experiment with just awesome statistics, just unbelievable statistics. Just, I mean, you can't plot them. I mean, you can't, right?
Yeah.
But there wasn't anything there.
Okay. When it's described in the prize citation, it sounds a little bit like a kind of rather discrete piece of discovery, but actually it was a longer term project. Really, it was a very thorough
Well, it's
job.
a project that goes from the early days at Stanford in 1954, when Hofstadter starts to measure how an electron scatters from a nucleus first, then the proton. We just keep going till we've measured everything that we can, and then later on we all go to DAISY, where they accelerate the proton. You don't use a fixed proton in the hydrogen, in a bucket of hydrogen anymore. You accelerate the protons and hit them to electrons and go to enormous ranges and try to see if there's anything new. And we didn't find anything new in Hamburg of that sort. And I'm still worried about whether we missed it or not, because it was 2 orders of magnitude in the variable that matters. So bigger range than we'd ever covered before.
And can you redo that experiment elsewhere, or?
That's finished now. Just finished, and never did find anything of that sort. That disappointed me. So, okay. No, we quit by about 75 or 76. We weren't doing that experiment anymore. We were doing another experiment because, let's see, in 1968, Weinberg came up with this weak interaction theory, unifying the weak and the electromagnetic interactions. And nobody paid much attention to it till de Ruckela and Tini, well, I can't remember anything anymore. But he and Tini showed that this was renormalizable, this theory, because everybody thought it was crazy. But it could be made to work mathematically, and so all of a sudden there was some interest in it. And then they discovered neutral currents, which is a symptom that this is actually happening. And one of the predictions is that in electromagnetic interactions there'll be a difference, because there'll be interference between the weak and the electromagnetic interaction, because the weak interaction is left-handed. And so you can tell by polarization experiments, okay? People did some, they said there's no effect. This was very hard on Weinberg's theory, right? What the hell's going on? It doesn't work, so on. And so there were, people were trying to fit this in, it's called parity conservation, how to conserve parity so the left-handedness doesn't change the experimental results. And so they did experiments, and actually this was a serious worry. And so one of my postdocs that came after we did the inelastic had heard from his theoretical friends, he was at Caltech at the time, that this was very important. And he went to a talk with somebody, by somebody who had built a source for the linear accelerator that made polarized electrons. And Charlie saw at once that you could do an experiment where you took left-handed electrons and right-handed electrons, and you scattered them, and they'd scatter differently because of the weak interaction. Okay? Now, the trouble is that this is a small effect. All right? It's 1 part in 10 to the 4th or less. So it's not easy to do that experiment. And so the source that already existed, it didn't look to me like it would work. So my contribution in that case was mostly as the brakes, not as the motor. You can't do that experiment until you show me how you can do it. I want 3 standard errors in a day so I can go and check and make sure that I'm really measuring what I think I'm measuring. Well, we never got there, but we did get to 3 standard errors in a week or even 3 days. And so we tried to do that, and that was an enormously difficult experiment and enormously satisfying because we made it. And in order to do it, I actually convinced the laboratory to let me run alone. That is, not share the beam with other users.
Because most experiments were shared experiments.
Well, all the experiments were shared, but no. And this was a time when Bert had his damn psi, and he was up the wall, right? And I was winning, and finally he was making so much fuss. I said, all right, we're going to make a test run, right? And in the test run, it'll be fairly short, and then you don't really care. But I'll tell you what we'll do. Every 2 hours, 3 hours, we have to turn off because we have to change some stuff in our source. And if you can get your machine filled in that gap when we're turned off, then we'll try and run like that. But you can't interfere. I mean, if you lose your beam 2 minutes into your run, tough one. You got to wait for the next time we go in, because I'm not going to I don't want anything, I don't want anything external, putting anything in. I mean, I stand on top of Hoover Tower, I look down at the students coming into Stanford, and I got to tell the difference between 1 more today and 1 less tomorrow. Right? That's hard.
That's a nice analogy. Yeah.
Right? So that's what I'm doing. And I can't stand anything. Right? I'm just scared to death of everything. And I got to measure all kinds of things and so on. So, okay, so we tried it, and it sort of worked. So then in the run, we did that. And then because we were so strict about the beam and the accelerator stayed in tune, and Bert was able to fill. And Bert had the best running he'd ever had. So by the end of the run, Bert was pushing for an extension to my run. He wanted me to keep running because he was getting better data than he'd ever had. So actually, since that was the other important thing that was going on, I mean, my conscience was even fairly clear that we hadn't wasted much machine time.
Which year was this?
77.
77. So
77 was the test, 78 was the experiment.
So it was just after Bert Richter had got his Nobel Prize, in fact. So,
Yeah.
he probably had some clout around the place just at that moment. Or maybe didn't matter.
Come on, Bert and I were at Heppel together. I mean, we have been friends and fought many, many times. Best fight was once when I went into an office about something and I was mad. He was director by then. I was mad, and I didn't know that he'd had a root canal that afternoon. That was a really good fight.
You couldn't be anything to his pain, exactly.
And so that experiment was really, and we found exactly what Weinberg said you should find, and the other experiments were wrong. So that one also won a Nobel Prize, but not for us, because the next year was Shelley and Weinberg and Abdus Salam.
I wanted to just touch, sort of to finish, if you like, on a couple of things. One is how the use of facilities has changed over the decades, that now there are more accelerators than there were back then, but there are still slightly more? No, it's the same.
Many fewer.
Okay.
When I first started in this business, every respectable university had their own accelerator.
Okay.
They didn't have, basically the Bevatron was almost an order of magnitude bigger than most people's experiments.
Right.
Right. So it was a huge factor of 5 over anything anybody else had.
Okay. So.
And then Brookhaven was a factor of 5 over them. We were on a separate path, right? We were less than 5% of the business.
But okay, what I was going to ask was that it's coming to a position where the big accelerators are the thing that people really need access to, and there are very few of those, and there is a bigger research community.
Yeah.
So how does competition for resources work these days? Is it likely that the breakthroughs are going to be very concentrated on these huge conglomerate research efforts?
Well, you have what you do is put everybody on the experiment, right?
But does that not limit the potential for individual kind of genius around the place if everybody's sharing?
I don't know. We'll find out.
Mm-hmm.
I would. Well, I tried when I was at CERN, because LEP, the electron-positron collider, that was in that tunnel before the LHC, that also had very large collaborations. And I went over there one night in the middle of the night, 4 o'clock in the morning or something. So there's only the postdocs around, the professors are all home. And I talked to them and said, how do you live in this? Because you don't have any control over what the hell is going on, right? How do you live? And they, as far as I could tell, they were all happy. And the answer is that they take some particular problem, and they're boss of that particular problem. They work on that problem, and they solve it, and that's where they get the satisfaction. And their expectations are lower about Stockholm, I guess. Although you couldn't get much lower than mine at that time. I wasn't.
No, but the satisfaction is coming from being part of the whole.
Yes. And having a piece that's your own. Okay. Now maybe that was true of us too. Part of the whole. I didn't build the accelerator, although I yelled a lot. And I started building the switchyard, and then that got taken over by the pros. And then we built the equipment for the experiment. And I was very lucky. I was just the oldest and the loudest. That's the only reason that I was the group leader.
Okay. On the subject of group leader, I wanted to ask you what you look for in people you brought into your group. Over the years, what have you tried to find in students and people?
I never had students. I had one student. I decided very early, from my experience here with the big accelerator, I decided it was not a good place for a student. A student has to do something where he can make mistakes. I can't, when my project costs millions of dollars, I can't let a student screw it up. So he doesn't get to behave and learn the way he should. So I concentrated on postdocs, which also need educating. And I'm very proud of my bunch of postdocs who are professors all around, here and in Europe and so on. But I only had one student, and the reason I took him was he came from Caltech. He was very smart, and he had worked with my collaborators at Caltech at another accelerator as a student, as an undergraduate student, and just blown everybody away. So he was better than most of the postdocs. So, okay, he did an experiment, and it's a long, complicated story, but I think he's happy, and I'm certainly happy. He was the man who created the satellite that's measuring high-energy gamma rays that was launched on June the 11th. Took him his whole life to get to the point where he had something which I consider his. No, not everybody does, but I consider it his idea. It looks just like what he brought me in 1991, saying, we ought to do this.
Goodness gracious.
Okay,
Yeah, so 17 years.
17 years. Hard work.
Good for him. He's a patient man.
No, he's not a patient man.
Okay, I suppose that's the secret, yes.
So I didn't have a bunch of students.
No, but in your postdocs, what did you look for?
Most of the postdocs were sent by people that I knew and trusted. And the postdocs that I interviewed, I ended up usually picking somebody from Caltech.
But
They really got fantastic education at Caltech.
right, but not so different from you then. If you basically but go on people's recommendations, it's the same as you when you came to Stanford.
Yeah, and then, well, I mean, interviewing people for jobs is an art. I mean, you let them talk, and sooner or later they'll hang themselves if they're not any good.
Mm-hmm. Very true. That sounds like a good point for an interviewer to stop talking, doesn't it?
So that was interesting. And at about that time, that second experiment was finished, the parity experiment, which I think was a real accomplishment. And that's professional pride is very high on that experiment, because a lot of people would not have done it as well as we did it. It wasn't just me, it's a whole bunch of people. But I kept saying it's got to be good. And to everybody else they wanted to get ahead. We had one real shootout. Some people wanted to do it in a much more simple way, with they would never have found the answer. But they looked good to the committee because they didn't need all the things I wanted. They didn't need the money. They looked good to the committee.
So how come you got your way in the end?
I don't know. I guess I was persuasive. I must have been. I mean, it wouldn't have taken much for an experimentalist on that committee to realize that the other guys weren't going to make it. But of course, the committee is half theorists, and half theorists don't have much appreciation for how hard something is. They just look to see whether they want to know the answer or not. And so, anyways, after that, I went upstairs as the research director. I didn't like it. I didn't like doing it. I don't know why. Some people said it was because I couldn't do just what I wanted anymore. But what I found was that I thought I'd had fun leading a group of people in the experiments, but they were all selected. They had selected me, or they didn't stay. I had selected them, or they didn't stay. And so we were mutually selected, and it was easy to get along. But when you're research director, you have to deal with people you don't like just as much as you have to deal with people that you do like. And I didn't like doing it. And I finally just quit. And never did much useful after that. I mean, I quit, and I did not take the group back, because the group by that time was being led by the man who was the moving force in that second experiment, the parity experiment. And he had the group, and he was plenty smart, and so I went off.
What year was this that you quit?
We're about 85 or something like that. I was on the LEP committee. I went to DAISY for a year, and I got involved with my French friends again on the experiment at DAISY that I told you about, that did not lead to more spectacular results in the electron-proton scattering. And I did some of that, but I couldn't be effective, because I'm effective on the ground. And just coming in now and again didn't get much done. And so those years, it was I worked hard on the LEP committee, probably did some good. And it was interesting to watch the experiment at Daisy. Mm-hmm. And then on this experiment with the satellite, I've not really been technically involved after the first 6 months or something. Right. Although I've been involved. I mean, I consider myself the group therapist. Even find myself asking, well, how do you feel about that? Just like a shrink.
Yeah, that doesn't sound like you.
I'm adaptable.
But that is quite a long time to say that you. I mean, obviously you have been doing lots, but you got the Nobel Prize in 90, and did that in a way change the way you felt about not being associated with a particular group? Because
it didn't change much at all. I mean, actually changed more in '89. In '89, I ran the international conference. That's a strong symptom that your days are numbered, right? And I also had a fairly serious malignant melanoma that year. So those are two things that probably changed my attitude more than the Nobel Prize the next year. The Nobel Prize was a lot of fun. And it was a lot of fun home after that because you're in a lot more things.
Well, that's really what I meant, that somehow it could be, and it is used by some people to sort of open a lot of doors and change direction, and they take on a lot more sort of public policy type things.
Yeah. Well, public policy, of course, was complicated for me because I stayed a Canadian. I came to the United States, and my mother was an American. We went to France. When we came home from France, in the embassy, they said, "You don't need a visa. Your mother was American." And I said, "Swell. How about a letter from somebody here? Because the guy on the desk, when I go into New York, is going to know what to do with that." They said, "Sure." They went upstairs, went to the lawyer, came back down and said, "Sorry, if you're born before 1935, you can only get American citizenship through your father if you're born abroad, not through your mother." I said, "Okay, you don't want me, I don't want you." All right, so I stayed Canadian. And then they revised the act, right, in about 1988 or something like that. And you can just see some female staffer in the senator's office reading this thing and realizing what it says.
Exactly, what happened to women in 1935?
And so all of a sudden they changed it, and I did not become an American by naturalization. I just went to the State Department and said, "Give me my passport." And they said, "Well, it's complicated, it'll cost you an extra $100. But that was the only complication. Well, that and proving that my mother had lived in the United States before she went to Canada. Yeah. We found her in the census.
So now you have dual citizenship.
I have dual citizenship.
So that would mean now you could. So.
But it meant that all those years when everybody else was fighting the Vietnamese War in Washington and consulting for the Defense Department, I didn't have to do that. So it's probably one of the reasons I succeeded was that I didn't split my time the way most of them did. But it also meant that I was never a Washington insider. I don't like Washington. Don't like Ottawa much, but that's mostly incompetence. Right? They're not evil, but they're not very smart. Washington, they're evil. And so I didn't. So I had not been involved a great deal in public policy, except through Henry, because Henry Kendall, on the other hand, was heavily involved in public policy all through those years. And of course, whenever he came here, he stayed in our house. He'd done that since it was built. And so, I mean, I would have long arguments with Henry, so I probably had influence, even though I didn't know it. Right? Although Henry's mind was hard to change.
But you've stayed in contact with Canada, and you still have quite a presence there. So,
I don't have much presence there. but I have done some things. That in fact is a major part of what I do now. I mean, your efficiency, as you get older, your efficiency drops down to where you get almost nothing done anyway, and so you have to be highly selective. And I got mixed up with some stuff in my home province, and I've worked fairly hard at that.
Do you think that's true about the efficiency and age, really?
Oh yeah.
Any thoughts on why?
Yeah, your mind goes, right? No, I remember talking to Felix Bloch once. He was about 70-something, and I don't know how it came up, but he said, oh yeah, jeez, I can't think anymore. And this is a guy who was really off scale. I mean, everything he did, his thesis, his postdoc, his first job, all of these founded fields of physics. Not great experiments in physics, but whole fields. Well, it was wonderful. When we were in Stockholm, they had a party for us at the Royal Academy. So my son went, and he took some bright young thing, pretty young thing from the Nobel Foundation to the dinner.
Lucky him, yeah.
So we had a dinner. And after dinner, well, I can tell you, I mean, at the dinner, I said, I didn't realize I was sitting on the wrong side of the hostess and had to say something. Okay, so all of a sudden at dessert, they told me I was going to make a speech in 3 minutes. And I started by saying, well, we've had a really good time tonight. I don't know whether it's because there's so many physicists here or so few economists. Okay? All right, so then we went on, and Ted came up and said, come on, Dad, this is pretty boring. Can we go home? Can the limo take us home and come back for you? And so I asked the driver. He said, sure. So he took Ted home. Okay, so this is maybe half an hour after the speech. Ted goes up the steps in the hotel. One of the economists from Stanford is at the top of the stairs. Says, hi, Ted. I hear your old man's been making fun of the economists again. So they've got a network that is really spectacular.
Or he was at the dinner and he got bored quicker and left fast.
No, he wasn't. He couldn't go to the dinner.
No, okay.
Physics. Who the hell at the physics dinner? Must have been. I mean, it has to be the driver, doesn't it?
I suppose it does, yeah. Well, if the drivers are there. But maybe they broadcast the dinner. Who knows? Anyway.
No. God, I hope not. Anyhow, those are crazy things. What he's interested in is what do you do when you've built the equipment? And the answer is all kinds of things are wrong.
Yeah.
Right? And you have to you then have to prove, and this is much more true in those days than it is today, but in those days you had to prove that what you were measuring is what you think you're measuring. So you have to make the target, you have to make sure the target, and we didn't, right? Our target was boiling, and so the density of the target was wrong. And we had fights over whether we could find corrections for it, or whether we had to do it again, and so on like that. You have to make sure your counters are working. You have to make sure the programs that you have. I mean, there was one, when we started to do the inelastic, okay, we've got this array up at the top of the spectrometer that measures the angle and the energy of the scattered electron. And you have to make from that a spectrum of the number of counts versus energy, right? And when we started to do that, nothing worked. There's garbage coming onto the screen. And one of the postdocs, who's now a professor out there, one of the postdocs spent 2 weeks, he must have worked 18 hours a day to rewrite the programs so that they would work. We had to completely rethink what was in that program in order to make it do what we really wanted it to do. And we didn't notice it until we actually started taking data.
So it's as far as you can get from the idea of just buying a bit of equipment, plugging it in and...
Oh no, I mean you have to show that the equipment does what you think it does. And you have to find out why it doesn't. Is there anything wrong, right? I mean, I was famous for making lists of things that might be wrong and how to check them, right?
Presumably there's also a need to understand every piece of the equipment, that not just the bit that you're
Yeah.
responsible for.
Well, there's a huge amount of calibration goes on. I mean, we use the electron beam steered through the spectrometer to make sure our optics are what we think they are. We measure the solid angle, the acceptance of the spectrometer by taking a beam in and seeing where it disappears as it goes right up the flue. I mean, you don't put a scattered electron in it, you put this electron beam of well-defined quantity in at the bottom and change the spectrometer settings and move the angle so that you map out what's up at the top, what the electrons are going to do starting from the target. So there's lots of stuff to do once the equipment's built.
And is that partly the fun of it? I mean, when a piece isn't delivering what you think it should be delivering, or you're not sure it is.
No, it's fun later when you decide that it does do what you. It's not much fun at all when you realize that things are scrambled and you have done something stupid, which happens quite regularly.
There must be some fun in that tinkering. I mean, it must be part of the attraction that you can tinker and get it right.
Well, I mean, we had in the second experiment, we had a thing where a pair of slits kept closing and breaking. And we couldn't figure out why. And we tested and tested and played and everything was perfect whenever we looked at it, and we'd go and ruin the damn thing again. So finally one night I said, okay, I'm going in there and I want all the interlocks on. Nothing gets turned off. Because when you go in there...
The interlocks, sorry.
Yeah, the interlocks are the things that prevent you from being irradiated, prevent you from being electrocuted, all those things. I said, I want everything off. Right? I want everything on the way it really is when we're running, and I'm going to go down there and watch what happens. So, it's a credible safety problem to do that. So they turn off the machine and they put a block in front of it. They do all sorts of stuff. And they make me promise not to touch anything and so on. And I go in and I stand there. And they turn on the magnets and the slits go bang. Right? And they won't let you in there when the magnets are on. Why do they do that? Because there's a relay somewhere. The relay's in the fringe field of the magnet. When you turn the magnet on, the relay closes. And it stays closed. Right? When you had a safety that opened the relay when the slits came together, but doesn't open the relay. So the motor keeps trying to close the slits and breaks them. So that's satisfying. I phoned Hobie at 3 o'clock in the morning and said, I found a problem with the slits. Yeah. What kind of instrument is a relay? And Hobie said, oh, shit. As soon as you thought of it, it was obvious. But it took a week to find the problem.
But it must take the sort of person who likes doing this stuff and who grew up doing it, the same sort of person who, frankly, blows their fingers off. Yeah.
Yeah.
Is it innate?
No, it's changed a lot because nowadays you build a detector and you use a computer to simulate what the detector does. So you try to understand the apparatus in the beginning, and you do all kinds of testing, much more than we could do, of the apparatus and the principles behind the apparatus before you start, and you use a computer. I mean, particularly the one in space, right? I mean, you don't get to fix it. So you have to be sure that it works, and you have to figure out what it's going to look like, and you do as much work as we did in our experiment, doing simulations, trying to say, what will it look like if I do this, and trying to make sure that the simulation represents the data. And so you take the apparatus and you run it in a beam at SLAC and see what happens. See whether you can predict what that's going to look like and whether that works. So, there's lots of skill, and lots of the skill is buried down 2 or 3 layers so that it's as automatic as the surgeon with stitches. But he had to learn to do that.
Yeah, I mean, that takes us back to this point of how important it is to learn to do that as a child, and as one limits the risks that children are allowed to take, how much inducement is there for kids to play and learn how to play in a scientific manner?
Kids will get around.
Yeah.
Kids will get around.
I mean, I've heard a number of laureates say that it's quite limiting that people aren't allowed to take as many risks as they used to be.
Sure, it's limiting, but in the days when you had a central computer and everybody had a terminal, and all the young physicists were spent their days looking at the terminal and doing calculations. B.J. Bjorkane coined the phrase terminal illness. Essentially, neither the theorists nor the experimentalists are going to get anywhere staring at that. Now, that turns out to be wrong. In fact, you can make the computer do things that you can't do, both in theory and in experiment.
Richard Taylor, it's been a great pleasure speaking to you. Thank you very much indeed.
Thank you.